Okay, for each part of this question, we're told that we have a 10 Newton particle placed on a smooth plane, and the smooth plane is inclined at 35 degrees to the horizontal. And in each case, there is a force which is keeping the particle in equilibrium, and we're going to look at three different ways in which that force could be acting. Now, the diagram is almost the same in each case, and in each case, we're going to have a normal reaction between the particle and the plane. The weight of the particle each time is 10 newtons, we're told that. And first of all, then, I've got the force which is holding the object onto the plane acting parallel to the plane. And it must be acting in an upward direction because otherwise the particle would fall down the plane. Okay, so let's work out the size of the force here. Now, all we need to do, because the particle is in equilibrium, we know that the forces which are acting up the slope must equal the forces which are acting down the slope. So forces down the slope. So let's actually look at what's happening here and what's actually and the forces which are actually acting in the first instance. Well, if we look, the only force which is actually making the particle go up the slope is this F, and the only thing which is resisting that is the component of the weight which is acting in the downwards direction. So going up the slope, we've got F. Acting down the slope, we've got the size of the weight, well, that's just 10, not 10g, just 10, and that's going to be multiplied by cos 55 degrees. So F is just, in this case, 10 cos 55 degrees, which comes out as 5.74 newtons in the first case. Okay, in the second case, the force which is holding the particle on the slope is acting horizontally, and it must be acting towards the right, because if it was acting towards the left, the particle would slide down the slope. So again, we're going to look at the forces which are tending to make the particle go up the slope. Well, that's not just F this time, it's actually F cos 35 degrees, because we're looking at the component of the force which is acting up the slope. So F multiplied by the cosine of this angle. Acting down the slope, again, we've got the component of the weight which is acting down the slope. In other words, 10 cos 55 degrees. In other words, F this time is going to be 10 cos 55 divided by the cos 35, and that comes out this time as 7.00 newtons to three significant figures. Third situation then is where this force that's holding the particle on the slope is at 25 degrees to the slope, and as it is in this diagram here. So let's have a look at the component acting up the slope. So this time acting in this direction, so up the slope, is F cos 25 degrees, because this angle here is 25 degrees. Acting down the slope, again, is the component of the weight which is acting in this direction, and so that's still 10 cos 55 degrees. So all we need to do with F this time is 10 cos 55 divided by cos 25 this time, and that comes out as 6.33 newtons. The last part here asks us, without doing any calculations, to work out where the normal contact force is going to be the greatest, and we can do that by realizing that because the particle is in equilibrium, that the forces that are tending to make it go away from the slope will exactly equal the forces that are tending to make it move towards the slope. Let's look at the situations. Now, in this case, R is just going to be the same as the component of the weight acting in this direction. So R is just going to be, it's only got one force, if you like, acting against it, and that's the component of the weight. This F is actually just parallel to the slope, so it has no effect on R. Okay, if we look at the second situation, R, which is here, is being acted against by both of these forces. So both of those are acting against R. And in this case, the third situation, R and F are both acting away from the slope. So the situation where R is going to be the greatest is this one, B, because R has got to fight, if you like, against F and the 10 Newton force. So R will be the greatest in the second situation, in other words, situation B.